Yeah, so this paper, it talks about carbon-aware scheduling, right? But it's mostly focusing on the CPUs, right? And what is the carbon footprint of a CPU or a job or task that may run, on a server that has a particular CPU, right? So, when they talk about scheduling, they talk about like software tasks, right? Like software jobs, machine learning, training, inference, any other software you could run, right? So, and what makes the server and the CPU like more efficient or less efficient, or more or have a higher carbon footprint or lower carbon footprint, right? So, what does it mean to have a carbon footprint? Uh, Owen, I'm gonna pick on you.
Okay. So I guess it depends on, are you defining process, are you including process or manufacturing in?
Exactly.
Yeah, well, because process or manufacturing is a fixed cost. So if you have something like an Apple M4, which uses slightly more advanced packaging, or if you have something like NVIDIA Blackwell on the GPU side, where they have really bad yields, so you're losing 30-40% of the things you produce. That means that you have sort of a higher fixed cost to offset in terms of like computation you need to do before a less efficient energy wise, but easier to use, or sorry, but easier to produce CPU would pull ahead.
Yeah. And this is the problem that this paper explores, right? So, we are talking about carbon-aware scheduling, and what this paper says is that we take into account that manufacturing carbon, right? Like all the energy that was used to produce a CPU and package it and ship it and whatnot, right? Like all of these activities in like making and distributing the CPU, they add to the carbon footprint, right? So, and that carbon footprint, apparently for even for CPUs, right? It's not small, right? And so this paper argues that traditionally, if you want to account for carbon footprint and try to, schedule your work in a data centers in such a way to minimize the task's carbon footprint, um, the traditional ways, they will account for that manufacturing carbon footprint of the CPU, right? So they specifically call out this metric called SCI, the software carbon intensity, right? So it's a metric that was introduced by the Green Software Foundation to quantify the rate of total carbon emissions per functional unit R, which in this case, this paper mostly looks at the CPUs. Um, functional unit are, I guess, yeah, they're talking about the software, right, running on a particular device. So the carbon emission for a given job consists of operational, denoted as O, and embodied, right? So that is the carbon emission that essentially exists just because this particular device, right, this particular server CPU was made and installed, and yeah. So, they give this, lovely metric, right? So essentially it's operational plus embodied carbon emission. And this embodied part in the traditional SCI metric is a fraction of, um, the device's like usage over the anticipated like lifespan, right? So if you project that, for example, a server is going to be operational for 5 years, your task, your whatever you're running, or a type of task you're running, you're going to run it for, I don't know, a month on this device. right? Maybe it's like a machine learning training or something. So, that's like 1 month over 5 year, right? So like in 5 year, you get like all of that embodied carbon out. So, that the cost of that tasks carbon like footprint is whatever the operational, like the energy consumed, and that 1 month over 60 months, right, worth of um, the total carbon emission that was used to manufacture that unit, that CPU. So that's kind of the big idea behind this SCI metric, right? Have the operational and manufacturing carbon accounted when you run software, right? And this paper makes a counter argument. They say it's not a good idea to actually take into account the embodied carbon emissions, right? Like once the device is made, you should only focus and purchased, right? Procured and installed in your data center. At this point, you should only make the operational decisions, minimizing the operational carbon, because you already have the device, right? Like that carbon is already in your data center, right? Whether you use it or not. So at this point, you better use the device if it yields better operational efficiency. So yeah, that's kind of the big idea of this paper, the big argument, right? This SCI metric may not be the best, and what they say is, it's like if you care about the carbon footprint, right, you should rather use just the operational part of the ACI, right? So they call it operational software carbon intensity metric. Um, and yeah, they claim that if you stick with it, you will actually end up using like you will end up using less carbon, right? So you will reduce your carbon footprint because based on their kind of mental experiments, and like a bigger case study in a like academic data center, they claim that the SCI metric actually results in the scheduling decisions, like how you decide which software to run on which server, that results in higher carbon footprint. Mm. So they have this little example here. They used they calculated the carbon footprint of two CPUs, right? One is older Intel Xeon, and another one is a newer Xeon. So both of them are the CPUs from Intel. I think they have, oh yeah, right here. So they have this two particular models, right? The older one is this one. They call it SA, and the new one is the Xeon Gold. They call it SB, right? And what happens, they benchmark it. They use the Passmark benchmark as kind of the illustration of the performance per carbon like footprint or per gram of CO2, right? So, and they also like estimated the carbon footprint of manufacturing manufacturing those CPUs, right? So, and what they say is, um, mm, if you normalize the carbon footprint of manufacturing and operating based on the score from the pass mark, so like how much grams of CO2 does this CPU, emit, right? For achieving each point in pass mark over a year, right? So let's say you have an application that is using the equivalent of one pass mark, performance point for a duration of a year, right? So this is going to be the carbon cost. So the embodied, that's the manufacturing cost, 0.11 gram per score year. and operational. So that's, the electricity cost essentially, right? 0.83. And, for calculating the operational one, they picked like one of the best possible scenarios, like a hypothetical data center in Sweden with access to very green electricity, right? So, you can see that this operational cost, it dominates, operational footprint, it dominates, right? But if you look at the newer machine, newer CPU, it's more efficient. It's faster and, it gets like better footprint per square year, but it was not as efficient to manufacture, and probably for the reasons that like Owen was describing, right? The yield is not as good. Intel was like struggling with adjusting to like newer process nodes and whatnot, right? So all kinds of things, right? The fact that it's a bigger CPU as well, right? So its operational footprint is bigger, and this is all like not operational. It's like embodied footprint is much bigger than the older CPUs. And it's based on the 5-year like lifespan of the device, right? So, and if you add these two together, right? If you add these two and this two, and use this as a metric to decide which machine to run your job, right? The older CPU is better, right? So this is what is shown in this table. If we use the SCI metric that combines both, you will choose, if you have a choice between the two devices, between the two servers, you will choose the older and slower server, and the server that is less efficient to operate because of the cheaper or smaller footprint of like manufacturing that device, right? So, and they call it the sunken carbon sunken carbon fallacy. Um, so, you already paid for this carbon. You already have this device. Why do you decide to run on the less efficient device and spend more footprint to operate? Right? Like you already purchased this device. That carbon is already like invested now. Your goal should be to amortize it as opposed to like ignore it, right? So what this leads to is like if you have the choice of these two servers, right? You will stick with the less efficient one, and that means that the more efficient one will be more idle, right? So you purchase the machine and it sits in there. The carbon cost for manufacturing that server and the CPU is there, but it sits in idle because of your scheduling decision, right? So you actually end up burning more CO2 than if you, have that same server who is sitting idle and you actually use it, right? So that's the argument here. The authors provide some, again, like calculations to support their point. And they say that, again, like depending on the server utilization or how much like embodied, carbon is in the CPU, but like let's look at the server utilization. Depends on the server utilization. You can get as much as 25% worse carbon footprint if you use that SCI metric that takes into account the manufacturing carbon, as opposed to just using a simpler metric which only takes into account the operational. Right. And this is because you are choosing to operate on less efficient and less green, right? More like higher emitting devices. Yeah, so they have this graph, they have a few other figures, and they have a very similar situation, similar graph from a real data center that they had. It's an academic data center. It's a small data center. We're not talking about cloud, but a very similar graph is like up to 30% worse carbon footprint if you use that SCI metric as opposed to just sticking to operational carbon. So yeah, I think at this point I'll just stop with my like, yeah, presentation, and maybe we can talk a little bit.